I will briefly report on some recent aspects of production additive manufacturing and properties of refractory high-entropy alloys. Co-authors are Mr. by so belonging to Teniovis and Katano-san from the University of Osaka. Very brief introduction of our company. We understand us as a leading global producer of tantalum and especially tantalum niobium powders. Here we are world market leaders. We have 4 production sites, 2 in Germany, Goslar and Lautenburg, 1 in Magdeburg, Thailand, and 1 in Japan, with a total of 670 employees and 400 active patents. One of our product lines is quite new, are so-called M.Weinmann powders. Those are specially developed powders for application in additive manufacturing processes. AM, of course, stands here for additive manufacturing, covering all relevant processes, laser power fusion, electron beam fusion, direct metal deposition, laser cutting, and intrinsic derived from intrinsic, indicating that we are introducing the properties, the desired or required properties of the final build already in the precursor materials, so in the alloy powders. This is done by producing pre-alloyed factory metal powders, usually according to customer requirements. All our processes, powders usually exhibit excellent processability. So historically, we started in 2015, of course, with very simple pure metals. Then we developed further, and today we are producing high entropy alloys and also metal ceramic composites. The materials we are dealing with, I mentioned already, are the refractory metals. So these are the early transition metals, group 4B, 5B, 6B. They are all characterized by very high or even extremely high melting points, which we also occasionally alloy with some main group elements. It's boron, carbon, aluminum, silicon. Boron and silicon help to improve strength. Carbon usually helps to improve the hardness. And aluminum improves the oxygen resistance by forming aluminum oxide scales. Okay, the problem with producing such materials are the high melting points, and usually there are no crucible materials available, which allows regular gas ionization, and this is why we are applying so-called electrode induction melting gas ionization. So the principle here is a contact-free inductive melting of either pre-alloyed rods or powder metallurgically produced rods, so abbreviated PM, and which are sometimes pre-alloyed by sintering, but this is not always necessary. Usually you can also produce simply pressed rods without sintering, because the process itself allows an in situ alloy. Accordingly, since you can start with PM rods, with powder mixtures, you have almost no limitations in materials compositions. So you can start with either elemental and go up to marginary. Depending on the process parameters, you can adjust the particle size and particle size distribution. Usually, we obtain dense spherical particles with good processability. And as I mentioned, in contrast to conventional atomization, there's no contamination of the powder with a crucible material. The principle of the setup is shown here. It consists of 2 major parts: the feeder and the central part and the cooling tower. So the rod is mounted to the upper part, then introduced into this coil. Here, an electric field is induced. Eddy currents occur, and these eddy currents heat the rod. The melt is then flowing downward, as is shown here. This is usually a 90-degree tip, so depending on the coil you're applying. Forming such a melt filament, this passes a nozzle, and thereby it's accelerated with hard gas and disrupted to form more droplets, which then solidify during the flight through the tower. The powders are then collected on the bottom or in a cyclone and further processed. The first thing that we do is, because we usually have quite a broad particle size, from very small to even scatter, we remove the very coarse fraction above 150 micrometers simply by sieving. So it's scatter of very big particles. The next step, what we're doing is we dispose the very small fraction below 10 to 15 microns, because the small particles, say, versus the particle flow. The rest, from 10 or 15 250 is then sieved into 3 fractions, one which is used in laser powder bed fusion, one which is used in electron fusion, so it's a 60 to 100, and one which can be used in laser cladding, for example, from 100 to 150. So we have 3 different fractions. The next step, if required, is a deoxidation process. This is a capability which is very unique at Teniovis, which we developed for tantalum capacitor powders, but this can also be applied for a lot of these AM powders, shown here, for example, for niobium. You see 2 pictures here. This is the powder as obtained after atomization, and this is the powder after deoxidation. What is done is very simple. We are treating these powders with magnesium vapor at 850 to 1000 degrees C. Magnesium reacts with oxide scales, thereby forming magnesium oxide. Magnesium oxide is enriched with hydrosulfuric acid, and thereby also these tiny particles which worsen the flow properties of the powders are removed, and you end up in this very nicely spherical particles. You can see the effective of the deoxidation. Here you have the different fractions, so SLM, EM, and LC. The oxygen contents of this niobium after atomization, and here the values after deoxidation. And accordingly, this deoxidation has a tremendous effect. We can even go lower, but then the particles get very difficult to handle because of salification and exposed to air. Okay, after having produced the powders, we very carefully examine the powders by chemical analysis, also physical methods, so the particle flow, particle size, everything, but also morphologically. This is usually done by light microscopy or electron microscopy. I will show you in the following slides a few examples. Here this is a ternary alloy, a titanium niobium tantalum powder with a composition. Here you can see this is spot 5 is the overall composition of the particle containing 77% of titanium. Remarkably, those powders do not form very homogeneous microstructures. There is a slight elemental demixing observed with the dendrite type features. So the dendrite type structures are blue, shown here, so composed of being enriched in niobium and tantalum, and the inner dendrite phase is enriched in titanium. So this inner dendrite phase is composed of 85% of titanium, and the dendrite phase is accordingly composed of 75% of titanium. A very similar finding is observed by investigating this MS85. I mentioned this powder. This is niobium-based alloy because this has a very high potential and is a frequently resonant moment for application in satellite thrusters, for example. Again, the SEM shows nicely spherical particles, and the ETX shows a demixing into a dendrite phase, which is here shown in blue. And this dendrite phase is enriched in tantalum and tungsten, as well as in the dendrite phase. These are the white spots, which is enriched in niobium and zirconium. Going to a really high entropy alloy, this is, for example, here this tungsten, tantalum, molybdenum, niobium, vanadium, equiatomic, so each 20 atom%. You can see again very nice and dense spherical particles, and again this dendrite type features. And again, the dendrite phase is composed of the high melting elements here, molybdenum and tungsten, so the group 6 elements. And the interdendrite phase is composed or is enriched in vanadium, niobium, and tantalum, so group 5 elements. Okay, the next step is we characterize our powders. So we go to printed powders. I do not explain this because everyone knows, but I would like to point out to the yellow box here. So it's very important to have a homogeneous printing process to deal with pre-alloyed powders, so no powder mixtures, because if you have powder mixtures, usually powders have different density, and when you're removing the powders, you have a separation of the light from the heavier element powder particles. Very important is also narrow particle size distribution for laser powder bed fusion, usually below 60 or 63 ppm, and an excellent powder flow, which is guaranteed by working with spherical particles. So this slide here shows you the results of printing this FS85, and I mentioned already a positive application is in satellite thrusters. One of such models is shown here. This was printed at our cooperation partner Alloyd in Oxford, and you could not only see the nice structural features such as our firm logo, but also these tiny channels here, so internal structures which are required for cooling once this thruster is in operation. The microstructure is compared here for the powder and the print, and this is what you already saw. This is the dendrite type structures with dendrite phase and interdendrite phase. And surprisingly, or surprisingly, remarkably, this structural features completely disappear once the material is printed. And the reason is the different cooling rates. With with laser powder fusion, you have much higher cooling rates than during the atomization. And accordingly, the system has no time to separate into this dendrite and interdendrite type phases. What you see, on the other hand, are clearly crystal, so crystalline domains, and the melt pool boundaries here indicated by the white arrows. If you go to the elemental maps, so tungsten, niobium, tantalum, and zirconium, you see that in contrast to the precursor powder, the elements are distributed extremely homogeneously throughout the sample, except from the melt pool boundaries, where you can see here in all images a very slight inhomogeneous distribution of the elements. But this is associated with different cooling rates of the elements, which is relevant, of course, at the melt pool boundaries. So this is an example for material which can nicely be printed. The next slide shows you an example. Is this epitomic alloy already presented, tungsten and the niobium, which is not easy to print, or which is very difficult to print. And the reason is, during printing, you are creating huge stresses which result in formation of cracks and pores, and usually it's even very difficult to remove the print from the substrate plate because it simply degrades. However, if you are able to remove it quite carefully, you can go ahead and hit. This was done here, for example, for this timer at 200 bars and 2000 degrees C. And what you see is that you more or less completely removed the cracks. This is quite surprising, because this is open structures. Nevertheless, we could remove, but what you see, there is residual porosity. The slides, the arrows are not there, but they should be. But the point is, you can effectively really remove the cracks and end up in dense and crack-free microstructures, but close porosity. If you're looking into the EDX images and electron microscopy images, you see that you have some segregations at the grain boundaries, crystal boundaries. Those appear in dark. And if you go into the elemental maps, so the EDX images, the element images, you can see there are two types of segregation. The first one are composed of oxygen, and if you compare this these images here, you can see that oxygen appears here in tantalum and vanadium. So we have vanadium and tantalum oxide species as grain boundaries. And on the other hand, you have segregations here of which are rich in vanadium, niobium, and molybdenum. Accordingly, we have two types of segregation: oxide segregations containing tantalum oxides and vanadium oxides, and elemental segregations being enriched in vanadium, niobium, and molybdenum. And the last slide I would like to show, this was already mentioned a couple of times today, is the difference of printing and casting. And this was done with this high entropy alloy. This is a biomedical high entropy alloy, which has very high strengths at room temp once it's cast, and extremely high strengths when it's printed. You can see here up to almost 2,700 megapascals. But the main feature I want to point out is the difference in the cast structures, where you see this standard type segregation, and this is due to this low cooling, so this low cooling rates or small cooling rates in comparison with a very high cooling rates of the additively manufactured species, where we have extremely homogeneous distribution of all constituting elements here pointed out for zirconium and tantalum. Finally, I would like the people who helped doing this work. This are, of course, our lab workers in our company, Thomas Otte, Martin Becker, and Frank Beerz at Aliovis. We have also a very strong M department on site. This is Chemalytics with Refractory, Thorsten van Bütten, Seville Basso. I would like to thank our team colleagues from Ellard at Oxford, and also Tomi Suhonen from BVT Finland for the cooperation in this one atom tantalum molybdenum tungsten and free cooperation. Thank you for attending the talk.